What's up everybody, and welcome back to another video on SAT Math from the Scalar Learning channel. This is part 4 in a 4-part series covering all of the categories and the critical concepts you need to ace the math section of the SAT. Today we are focusing on the last of 4, which is additional topics in math. Without further ado, let's get into it. First, we're going to be talking about volume word problems. So volume word problems are going to require that you need to know certain volume formulas, and the key objects that you need to know the volume formulas for are as follows. First, we have a sphere, which is essentially just a ball. You can see the key component of a sphere is its radius, and we use that in the formula as follows. The formula for the volume is 4/3 times pi r cubed. Next, we have a cylinder. A cylinder is like a can of Coke. All right, and the key components here are the radius of the base as well as the height. To get the volume here, it's pi r squared times the height. Next, we have a prism. So what is a prism? A prism, we could have a rectangular prism. We could also have a triangular prism. It's essentially a particular shape reflected across or extended across that whatever the length of the height is. And what we want to do here is calculate the area of that base and multiply it times the height. Next, we have a pyramid. A pyramid can be any shape for the base extended to a point at the top. So there we have a square pyramid. Here we have a hexagonal pyramid. Again, the formula is simply 1/3 times the area of that base times the height. When we look at the volume formula for a cone, it's actually very similar, and a cone looks similar except for it's a circular base and a point at the top. So again, we see that 1/3 cropping up again times pi r squared times the height. And the reason why I say it's similar to a pyramid is because pi r squared is the area of the base. It's the area of that circle at the bottom. Now, when we look at these volume formulas, it is very important to note that you don't have to have those memorized because they are at the beginning of each of the math sections in this reference sheet. So you can see we have a rectangular prism, a cylinder, a sphere, a cone, and of course a pyramid at the far right. So those formulas are there. You don't have to memorize them. I think it's good to be familiar with them and understand them, but know where they are on the test. Probably the most important formula when it comes to right triangles is Pythagorean's theorem. So Pythagorean's theorem is a squared plus b squared equals c squared. I'm sure you've heard it many times in math class. And what does that represent? That relates to a right triangle where a and b are the legs and c is the hypotenuse, which is the longest side that is opposite the right angle in that corner. And what this really means is if I were to square all those values, the area of square A plus the area of square B always will equal the area of square C for any right triangle. So now if we take an example of some values for a specific right triangle, the most famous one, a 3, 4, 5, the leg would be 3, the other leg would be 4, and the hypotenuse is 5. And this of course fits the formula because 3 squared is 9, 4 squared is 16, 5 squared is 25. 9 plus 16 does indeed equal 25. Now let's take another example where we're going to use Pythagorean's theorem to solve for a missing side of a triangle, and in this case the hypotenuse. So here we have the formula at the bottom, a squared plus b squared equals c squared, and what we're going to do is we're going to take our right triangle and notice that there's a square in the bottom left corner. That denotes that that's a right angle. There's your 90-degree angle that makes it a right triangle. And then 5 is a leg, 12 is a leg, and that unknown c is the hypotenuse that we're trying to solve for. So we're going to plug these values into the formula and check out what we get. So we get 5 squared plus 12 squared equals c squared. Now we're going to solve for c. So what is 5 squared? It is 25. 12 squared is 144. Now we're going to add those two together and we get c squared equals 169. Next, we're going to take the square root of both sides because I don't want c squared, I want the value of c. So what is the square root of c squared? It's of course c. Square root of 169 is 13. Boom, done. Now we're going to come to another example where we're not solving for the hypotenuse, but we're solving for a missing leg. So again, we've got a right triangle up here. We know that one side is 7, which is a leg. We know the hypotenuse is 25, but our b side is missing. We don't know what b is. Same thing, we're going to plug in and isolate just like before. So I've got 7 squared plus b squared equals 25 squared. 7 squared is 49. 25 squared is 625. Now we're going to isolate b squared. Let's subtract by 49 on both sides. I get b squared equals 576. Last but not least, let's take the square root of both sides and we get b equals 24 because of course 24 times 24 is 576. So our missing leg in this case is 24. Next, we're going to move on to something called the triangle sum theorem. This is so fundamental on this test, and this theorem states that if we have a triangle, doesn't matter if it's right, acute, obtuse, scaling, isosceles, doesn't matter, always fits this rule. And we have 3 angles for this triangle. The sum of these 3 angles will always be 180 degrees. That is an invariable truth, so you can always rely on that rule on the test. A corollary to this rule is if we have a right triangle, okay, so again, one of the angles is 90 degrees. We know that the remaining 2 angles must add up to 90 degrees. Why is that? Well, if we have a right triangle with already a 90-degree angle and the others 2 add up to 90, the sum of all 3 therefore is 180 degrees. So you know, anytime you got a right triangle, the remaining angles, other than the right angle of course, are complementary. Next, you want to be familiar with special right triangles. Special right triangles, there's 2 of them. They're also on that reference sheet that I showed you above, so you don't have to commit this fully to memory. But special right triangles come in 2 flavors. The first one is a 45-45-90. Now in a 45-45-90, you can see that 2 of the angles are equal, therefore it's an isosceles triangle, so we can represent the 2 legs as x, they're both equal. Then if we look at the hypotenuse, it's always going to be the leg times the square root of 2, so x times a square root of 2. The other flavor is a 30-60-90 right triangle. So here, the smallest side is going to be opposite that smallest angle, and that is our x value, okay? If I know that that's x, I know the side opposite the 60-degree angle is going to be that side times the square root of 3. So in this case, x times square root of 3. Last but not least, the hypotenuse is double that little leg, so it's going to be 2x. In the 30-60-90, it's important to note that that smallest side, the side opposite the 30 degrees, is always the most important side because it helps us derive the other 2. Now I'm going to give you concrete examples of these special right triangles with actual values. So again, we're going to remember that a 45-45-90 has x radical 2 for the distribution of the sides. First, we're going to start with the given that the length of the legs here are both 3. So you can see that these correspond with the x's, right? Because they're the legs. So what must be the hypotenuse? The hypotenuse is of course the length of the legs times square root of 2, aka 3 square root 2, and you see that matches up with the hypotenuse down below. Now let's talk about the 30-60-90. We have the example there at the bottom, and let's take a real example. We've got 30-60-90, and they give us the smallest side, which is of course 6. So since the 6 matches up with the x, right, because it's opposite those 30 degrees, I know that the medium leg opposite the 60 degrees is going to be 6 times square root of 3. So you can see that matches up with the x root 3 at the bottom. Last but not least, we've got the hypotenuse, which is going to be double the little leg, meaning 2 times x, or 2 times 6 in this case, which is 12. And you can see, of course, that links up with the 2x at the bottom. Next, let's move on to congruence and similarity. First, let's define what is congruence. Congruence just essentially means that 2 shapes are identical. So for example, if I've got a pentagon, a congruent shape to that would be the identical pentagon. Same with this octagon here, an identical shape would be another octagon that looks exactly the same. These are congruent shapes. All of the corresponding sides are equal, and all of the corresponding angles are also equal. Now let's contrast that with similarity. So similarity means proportionate. A lot of times if you take a picture, you put it in a scanner or a copier and you enlarge it, that's called creating a similar object. You're keeping it proportionate, but you're either expanding it or shrinking it. So in this case, if I have a pentagon here, a similar shape would be that same pentagon but expanded. Likewise, if we take this octagon here, of course a similar shape could be a shrunken octagon. So again, the sides are all proportionate, but the angles, by the way, for similar figures are all going to be congruent. It's not like we shrink the angles are all identical, but the sides are proportionate. Now when we talk about congruence, a big focus on the test is going to be congruent triangles, determining if triangles are congruent, and then saying, all right, well now I know they're congruent, I can match up corresponding sides to say that certain sides are equal to other sides. But how do we show that triangles are congruent? There's 5 key ways, 5 key theorems. First, we have side, 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 meaning if I can show that all 3 sides of 2 triangles are equal, they have to be equal in every way, which means that even the angles are also equal. Next is side, angle, side, which shows if I can show that a side, then an angle, then the next side over is also congruent, then the two triangles must be equal in every corresponding way. Now it's important that you note that that angle is sandwiched between those two congruent sides. It's gotta be in that particular order. Next we have angle, side, angle. So again, I showed two angles and a side, and it's important to note, once again, that side has to be sandwiched between the two congruent angles for this theorem to hold true. Next we have angle, angle, side. So here we have two congruent angles and then a third side out there. Angle, angle, side is another way to show that two triangles are congruent. Last but not least, we have hypotenuse, leg. This only applies to right triangles. So you can see that there's those little boxes in the left-hand corner that shows that both the triangles are right. And if I know that, and if I can show that we have a leg that's congruent and we also have the hypotenuses are congruent, we know that these two triangles are congruent through and through. Next, let's talk about similar triangles. So similar triangles, there's three theorems that can show that two triangles are similar, which means that they are proportionate. Again, right? The sides are proportionate, but the angles are all equal. So first we have angle, angle. If I can show that two angles in any two triangles are congruent, I know that the triangles are similar, which means all three angles are equal and all three sides are proportionate. Next, I have side, angle, side. So in side, angle, side, I have to show that two pairs of sides are proportionate and the angles in between those sides are congruent. So again, in this case, for this to hold true, since A and X, those two angles are congruent, I have to show that AB is proportionate to XY and AC is proportionate to XZ. Then we can prove side, angle, side similarity. Finally, I have side, side, side similarity. So if I can show that all three pairs of corresponding sides are proportionate in the same way, like they form a 1:3 ratio or 1:4 ratio or whatever, then the triangles must be similar and all the angles therefore must be congruent. Now let's move on to right triangle trigonometry. This is probably considered the most advanced topic on the test. Trigonometry on the SAT comes down to SOHCAHTOA. Okay, it's all about SOHCAHTOA, it's all about this acronym. If you can understand and apply this acronym, you're pretty much good to go. So what does SOHCAHTOA stand for? Let's break it down. First of all, the S, C, and T stand for sine, cosine, and tangent. These are functions that deal with ratios of sides for right triangles, all right? So now we have this right triangle here. What is the O and the H? That stands for opposite and hypotenuse. That tells me that if I'm taking sine of an angle down there, sine of angle A, it equals the length of the opposite side over the length of the hypotenuse. So you can see it's all color-coded, right? What about cosine? The CA, it's C-A-H. A stands for adjacent, H again stands for hypotenuse. So cosine of that angle A equals the length of the adjacent side, that brown side, over the length of the hypotenuse. Last but not least, we get to tangent, TOA. Again, we already know that O stands for opposite, A stands for adjacent, therefore tangent of A equals the opposite side, length of the opposite side over the length of the adjacent side. Now let's look at SOHCAHTOA with a concrete example. So again, I'm going to put up that SOHCAHTOA picture at the top right. So let's say we got a right triangle. It's got to be a right triangle, by the way, to apply these ratios. And we've got our angle there, which we're going to call theta. And we've got these following side lengths, 5, 12, and 13, which is the hypotenuse. I'm going to show you how to apply these trigonometric functions based on theta. So if I took sine of theta, it would be 5 over 13. Why? Because 5 is opposite of the theta and the 13 is the hypotenuse. Cosine of theta would be 12 over 13. Again, because 12 is adjacent to theta, next to theta, and 13 is again the hypotenuse. Last but not least, tangent of theta is going to be opposite over adjacent. Opposite of theta is 5, adjacent to theta is 12, so we get 5/12. Another rule that the SAT loves to test on when it comes to trigonometry is that sine of x will always equal cosine of 90 minus x. This means that sine of an angle will equal cosine of that complementary angle. So what am I talking about? Sine of 10 will equal cosine of 80, because you can see those two are complements, right? 10 plus 80. Likewise, sine of 30 will equal cosine of 60. Sine of 45 will equal cosine of 45. And our last example here is sine of 70 equals cosine of 20. Something else that the SAT loves to test on is the signs of sine, cosine, tangent based on quadrant. So I want to talk about that as well, so you're not thrown off if they try and get you on one of these questions. So what am I talking about quadrants? So we're talking about the X, Y, we're talking about the coordinate grid, and we notice that up here is the first quadrant, second quadrant, third quadrant, and fourth quadrant, okay? And when I'm talking about taking these trigonometric functions in these quadrants, I'm now using the same XY grid to break up angle measures. So what do I mean by that? I mean that if you're taking the sine, cosine, or tangent of an angle between 0 and 90 degrees, you're in the first quadrant. Between 90 and 180 degrees, you're in the second quadrant. Between 180 and 270, you're in the third quadrant. And between 270 and 360, now you're in the fourth quadrant. Let's say you get to 361, then you're back in the first quadrant, and so on and so forth. So it's kind of like a clock going counterclockwise. To help you remember the signs when using these trigonometric functions in various quadrants, we've got this really cool saying. All students take calculus, okay? So what does this mean, right? The A stands for all, and that means all trigonometric functions in that first quadrant are always going to give you a positive value. In quadrant 2, that relates to S because of students, which of course corresponds with sine, which means that sine values in the second quadrant are positive. So because we said everything in the first quadrant is positive, sine is going to be positive in both the first and second quadrants. Next, take links up, of course, with tangent. So tangent is going to be positive in that third quadrant with degree values between 180 and 270 degrees. And finally, calculus relates to cosine. Cosine is going to be positive when you're taking angle measures between 270 and 360. But again, sine, cosine, and tangent are also going to always be positive between 0 and 90. Now bringing that grid back up, we're going to look at some concrete examples. So for example, sine of 120 is going to be positive because we're falling in that second quadrant. But sine of 195, whatever the value will be negative because that falls into the third quadrant. Sine is not positive in the third quadrant. Next, we've got tangent of 220. Again, we're in that third quadrant. That's the golden zone for tangent. It's going to be positive. But if I took tangent of 330, which would land me in the fourth quadrant, that would be a negative value. Finally, for cosine, cosine of 335 in the fourth quadrant, positive output. But if I did cosine of 135, that would land me in the second quadrant, which would give me a negative value. Now we're on to the section involving angles. First, I want to start by explaining what are complements. I know I mentioned that previously. Complements are any two angles that add up to 90 degrees. So if we looked at a 90-degree angle split into two angles, if that were X and that were Y, those would be complements because together they make a 90-degree angle. An example of two angles that would be complementary are 15 and 75 and also 30 and 60 because both of those pairs add up to 90 degrees. Another important term is supplements. Supplemental angles are angles that add up to 180 degrees. So if I have a straight line that comprises of two angles, W and Z, W and Z will of course be supplements. Examples of supplementary angles include 30 and 150. Again, they both add up to 180. And last but not least, 95 and 85. Moving on with the angle section, we also want to be super familiar with parallel lines and all the angles that come with parallel lines. So we're going to throw up some parallel lines here and we're going to cut it with a transversal. Transversal is just any line that cuts two other lines. In this case, it's really interesting when it's cutting two parallel lines. Now we're going to throw up some angles here. We got 1, 2, 3, 4, 5, 6, 7, 8. So there's different angle pairs that are formed when we have two parallel lines cut by a transversal. First, we have corresponding angles, and these are congruent angles. Corresponding angles will include things like 2 and 6 and 4 and 8. Notice how it almost looks like to get to 2, that 6 just slides up the transversal. So they're sort of situated in similar places. So 2 and 6 are corresponding, 4 and 8 are corresponding. Also, we have 1 and 5 and 3 and 7. So every pair of corresponding angles are going to be congruent, and it makes sense. They look like they're equal. Next, we have alternate interior angles, and these are also going to be congruent. Alternate interior, we call them interior because they're on the inside of those two parallel lines. And so we can see here we've got 4 and 5 are alternate interior angles, as well as 3 and 6 are alternate interior, and each of those pairs are congruent. Next, we have alternate exterior angles, and these are also going to be congruent angles. These are going to be on the exterior of those two parallel lines. So we've got 1 and 8, and then we've also got 2 and 7, and notice once again 1 is congruent to 8, 2 is congruent to 7. Next, we've got consecutive interior angles. So interior means that they're on the inside of those parallel lines. Consecutive means right next to each other. So we've got 4 and 6 right there, and these aren't congruent, but they are supplementary, meaning they add up to 180. Another pair of consecutive interior angles would be 3 and 5, also adding up to 180. Last but not least, we've got vertical angles, and vertical angles are going to be across from each other, and they are always congruent. So for example, we've got 1 and 4. You see how they're kind of across from each other based on that X. And we've also got 2 and 3. And then we've got another set. We've got 5 and 8 are vertical angles, and 6 and 7 are vertical angles. So remember that, and that's probably the most important one. Vertical angles are always congruent. Another thing we got to be aware of when it comes to angles is this other measurement called radians. Degrees and radians are just like Fahrenheit and Celsius. They're just two different units of measurement. We look at 0 degrees, it actually is also 0 radians, but then we get 30 degrees is equal to pi sixths, 45 is equal to pi fourths, 60 degrees is pi thirds, 90 is pi halves, 120 is 2 pi thirds, 135 is 3 pi fourths, 150 is 5 pi sixths, and of course 180 degrees is pi. So these are some common ones that it's not such a bad idea to get familiar with them, but you don't need to. I just want to put them up for your reference, because if you can convert between degrees and radians and vice versa, you're good to go. So the formula to convert from degrees to radians is you take that angle and you multiply it by pi over 180, and that makes sense because pi is equal to 180 degrees. To convert from radians to degrees, you take the angle measurement and you multiply it by 180 over pi. Now, the good news is you don't necessarily have to memorize this per se, because they do tell you at the front of each of the math sections that pi radians equals 180 degrees. So you can use that to come up with this unit ratio, but these are the formulas if you want to memorize them. Next, we come to circles, and this is obviously a really big part of the SAT. So we're going to go through all of the terms that you need to be familiar with just to understand everything that's going on with these types of questions. So first we have our circle here, and we have the circumference. That is the measure going all the way around the outside of a circle. Next we have the center, which of course is in the center, but still an important point nonetheless. Now we have a radius. The radius is a line segment that goes straight from the center out to the outer edge of a circle. Super important to know what the radius is, and it's going to be the same no matter what point of the circle it touches. Next we have the diameter. The diameter is a line segment that goes from one edge to the other of a circle but goes through the center. Next we have a chord, which is just a line segment that goes from one edge of the circle to the other. But notice that a diameter fits this description. A diameter is indeed a chord, it just goes through the center. Next we have a sector of a circle. A sector of a circle, it's like a slice of pizza, right? If you draw lines out from the center and we kind of cut out a chunk or a slice, that is a sector. Next we have a secant. A secant is a line that cuts through a circle. Next is a tangent. A tangent is a particular line or line segment that touches a circle just at one point, but it's important to note that where it touches the circle, if a radius touches it at the same point, it forms a right angle with that tangent. Last but not least, we have a segment, which is a chunk like this. It kind of looks like the crust of a pizza slice. It's basically the area that is created when you have a chord come across and you're not going up to the center, right? So that's why it looks like a little bit different from a sector. So there you have it, that is a segment. Next, we're going to talk about some key formulas when it comes to circles. First of all, we want to know how to calculate the circumference of a circle. Circumference equals 2 pi times the radius. Another common measurement we're going to have to take on the SAT is the area of a circle. We take the area of a circle by doing pi times the radius squared. In addition to these formulas, we need to know how to take part of the circumference or part of the area, and we need the following formulas. So here, this is called arc length, okay? Arc length is just a piece of the circumference. Again, like a piece of the crust as opposed to the entire crust of a pizza. The formula for this, you'll notice, looks similar to circumference. It's 2 pi r, which is the circumference, but all you're doing is you're multiplying by the fraction of that central angle n over 360. Likewise, for the area of a sector, we're taking the area of the circle, pi r squared, but we're multiplying it by that same fraction, the central angle over 360 degrees. Next, we're going to talk about arc measure. Now, arc measure is a little bit different than arc length. Arc length is a specific value of length. Arc measure is again going to be in degrees or radians, just like a central angle. So as I mentioned, it can either be in degrees or radians. It's equivalent in value to the central angle, and it's double the value of an inscribed angle. So let me show you what I'm talking about. Let's say we have a circle. We have 3 points here. O is the center. And we have this arc, which is arc AB, okay? And if I cut it out like this with lines extending so I can create a central angle, what I know is that if the central angle AOB measures 50 degrees, guess what? The measure of arc AB is also 50 degrees. Likewise, if I have another circle and I've got these 4 points, we're really not going to use O in this example, but let's say I got AC, AB, and C. If I have an arc that is arc AB, and I'm going to create these lines again so I can have an angle that is, this is an inscribed angle, by the way, which is coming from the circle, not coming from the center. If the angle measure of ACB is 25, the arc measure of AB will be double that, which is 50. Continuing on with circles, but on the coordinate plane, we're going to talk about the very important circle equation. I always see 1 or 2 questions involving the circle equation, so you gotta commit it to memory. It is x minus h squared plus y minus k squared equals r squared. Okay, so what are all these pieces? The center value is hk. That is the coordinate of the center. So you notice that that's minus h, but it's positive h. Notice that that's minus k, but it's positive k. So that's where we derive the center coordinate. And that r squared, that is the value of the radius. So if we have 25 or if we have 36 on that side, it's going to be the square root of those values will give us the radius. So if it's 25, it's 5. If it's 36, it's 6, so on and so forth. Looking at a circle, we can see that there's that center coordinate, h comma k, and of course there is the radius in purple. Continuing on with the concrete example involving the circle equation, which I'll put at the bottom there, we can see here we've got x minus 3 squared plus y minus 4 squared equals 25. So in this case, my center is 3 comma 4. We're flipping those values, right? It's a negative 3, becomes positive, so on and so forth. And the radius is 5, not 25, it's 5 because we have to take the square root. And if I plotted this on a coordinate grid now, we'll see the circle is like that with a center at 3, 4 as we predicted, and a radius with a length of 5. When it comes to the circle equation, you also need to be prepared for the cases when they're not in that nice format. So what we're gonna have to do here is get it to that nice format at the bottom. So let's say we've got x squared plus 4x plus y squared minus 8y equals negative 11. Now I know this is a circle because I've got both of those values are squared, and they're not going to give you ellipses or other things like that on the SAT. I need to use a technique called completing the square to get it into the right format. So first I'm going to rewrite it like this with a little bit of spacing. So I'm going to separate those x's, separate those y's, and keep that constant over there. So how do I complete the square? For the x's, I look at that b term, which is 4, right? Because it's multiplying just the x, not the x squared. And I say, what is half of 4? Well, that's 2. And then I take that 2 value and I square it, and I get a positive 4. And I'm going to take that and I'm going to add it to this side. But I can't just add to the left and not to the right. So I'm going to add a 4 to the right side as well. Next, I'm going to do the same thing with the b value of the y. So same thing, it's a negative 8, not a positive 8, not that it matters, but it is a negative 8 in this case. So I'm going to follow that same step. I'm going to say half of negative 8 is negative 4. I'm going to square negative 4, that becomes 16. So I'm going to add 16 to this side, but I must do the same to the right side. So I got 16 there as well. Now on the right side, you can see I've got 16 plus 4 plus negative 11. We're going to combine that in a second, but first I want you to notice that on the left side, I've got this really nice perfect trinomial that is a perfect square. I've also created this nice trinomial that's another perfect square. That's what we want. That's why this is called completing the square. All right, so moving down as we simplify, I'm going to factor those two guys. And on the left, I got x plus 2 times x plus 2, like I said, perfect square. And the other one, I got y minus 4 times y minus 4. And on the right side, that simplifies to 9. Now I'm going to rewrite it one more time. And guess what? We're in our perfect circle equation. Now I can finally graph this on a coordinate plane because I've got a center at negative 2 comma 4. Again, we're flipping it, so it's a positive 2 becomes negative 2. It's a negative 4 becomes positive 4 with a radius of 3, right? Because it's the square root of 9. And there we are done. Next, we're going to talk about complex numbers. So complex numbers is the largest universe of numbers, but really when they're talking about complex numbers on the SAT, we're talking about the imaginary part, which is I. So what is I? I is the square root of negative 1. Why do we call it an imaginary number? Because normally we're trying to take the square root of like 4, for example. It could be 2 or negative 2. The square root of 9, which could be 3 or negative 3. Square roots of negative get a little tricky because there is no real number that when it multiplied by itself gives you -1, right? 1 times 1 is 1. -1 times -1 is 1. So we're at an impasse, but they are important numbers in the real world nonetheless. That's why we kind of created this term I to represent the square root of -1. So it's important to know this fundamental piece. Next, it's also important to note that I squared is -1. Now that makes sense, right? Because if I'm squaring a square root, the square root just goes away. Well, what if I took I to the third power? It becomes -I, because we're now doing -1 times I, which of course is -I. And last but not least, I to the fourth is +1, because now we would get -I times another I, -I squared, which is -1, right? So it brings us back to 1. So these 4 values are really important to know, and they're important to know because the cycle continues. So check this out. Then if I go to I to the 5th, back to I to the 6th, back to -1, I to the 7th, -I, and I to the 8th is 1. So it kind of repeats in this 4-part pattern. The way to shortcut this is if I got like I to some random number, if I divide it by 4 and I have, let's say, a remainder of 3, okay, that means the value is going to be -I. If I divide it by 4 and have no remainder, right, it goes in evenly, it's going to equal 1, so on and so forth. So if we look at another group, right, I to the 9th is I, because if I divide it by 4, I got a remainder of 1, that's just I. I to the 12th is 1, again, no remainder when I divide 12 by 4, and I get a nice 1. So just remember, this pattern continues indefinitely. Now if I were to look at some of these examples, if I had an equation here that was 5 plus I squared, it would equal 4. Why? Because I squared is -1, 5 plus -1 is indeed 4, and here we have 7 plus I to the 8th equals 8. Why? Because I to the 8th is 1. Of course, 7 plus 1 is 8. When dealing with these imaginary numbers on the SAT, you want to, in large part, think about them as variables unless they are taken to a certain exponential power. When it's just the power of 1, treat it like a variable. So for example, if you're given something like this where they say simplify 2 plus 7i minus 3 plus 4i, treat it just like an x. So first I'm going to distribute that negative, and I got 2 plus 7i minus 3 minus 4i. Now I've got like terms here, right? I got a 2 and a -3, combine that, you got a -1. Then I got a 7i and a -4i, combine those, and it's a +3i, boom, done. In this next example, we've got 3 minus 6i plus 2 plus 8i. Here the parentheses aren't doing much because we've got a plus in between them, so we're just going to remove those parentheses. And again, link up like terms. 3 and +2 is a 5, -6i and 8i is +2i, boom, done. The last thing you got to know about imaginary numbers is if you're given them in a fraction format, we do not want imaginary numbers in the denominators. It's just like if you had a square root in the denominator and they ask you to simplify, you know your main objective is to get rid of the square root in the denominator. So let's say we got something like this. We got 3 plus 4i over 6 minus 5i. Okay, this is kind of a tricky one, right? If we just had an I in the bottom, we can multiply it by another I. It would be I squared, which is -1, is gone. But here we've got a tricky one. We've got essentially a binomial. How do I get rid of the I here? Just like with square roots, we multiply by the conjugate. So what is the conjugate? It's the same as 6 minus 5i, but it's 6 plus 5i. And I gotta have it on top as well because we need that fraction to equal 1. Otherwise, we're fundamentally changing the value of this expression. Now, how do I simplify? We're going back to basics. We are going to FOIL it out. So first, we're gonna do the first terms, which is 3 times 6, which gives me an 18, and 6 times 6, which gives me 36. Next, we're gonna do the outer terms. We're gonna do 3 times 5i, which is 15i, and 6 times 5i, which is 30i. Next, we're gonna do the inside terms. 4i times 6 on top gives me 24i, and -5i times 6 gives me -30i. Finally, we're gonna do the last terms, which is 4i times 5i, which is 20i squared. Don't forget that squared, right? Because I times I is, of course, I squared. And on the bottom, we got -5i times 5i, which is -25i squared. Now, you'll notice immediately that on the top, we've got like terms that we're going to combine, and same with on the bottom. But on the bottom, you notice that it's a +30i and a -30i, which means they're going to cancel out. That's why the conjugate works. The i's are gone. Now you might be saying, all right, there's still an I squared, but that's gonna resolve in a second, and I'm gonna show you why. I squared equals -1. We learned that on the last slide. So now let's see what happens as we combine like terms and simplify further. So first, we're gonna combine that 15 and 24i on top to get a nice 39i. 18 stays as 18. What happened to the I squared? Since it's really -1, that's a -20. Likewise on the bottom, those middle terms canceled out, and we got 36 plus 25. Why? Because that I squared became -1. So once again, the negatives cancel out and it's a positive 25. Last but not least, we combine like terms on top and I get -2 plus 39i, right? 18 minus 20 is -2. And we got 36 plus 25 on the bottom, which is of course 61, and we are done. That is it for this final installment of critical concepts needed for the SAT math portion. I hope you enjoyed this series and I hope you enjoyed this video in particular. And if you did, please click that like button. If you want to see more from the Scalar Learning channel, make sure to click subscribe. Thank you so much for joining, and I'll see you in the next video. Take it easy.